Eric is a research scientist at the University of Colorado Boulder, and he studies 3D modeling of extrasolar planet
Is
atmospheres.
let's see. Hopefully this is showing up all right.
Yep, we see it.
All right. So thank you all for having me talk. And sorry I haven't been around this week. Mike Way, who most of you know, has been out visiting me here in Colorado. So the title of my talk is ExoCAM, a 3D climate model for exoplanetary atmospheres. So ExoCAM, what is it? ExoCAM is a model extension for the NCAR Community Earth System model, and it facilitates a variety of exoplanet climate modeling applications. It's installable on top of CESM version 1.2.1, and ExoCAM contains source code modifications, initial files, name lists, which are runtime text files, which are input for configurations. So utility scripts, analysis scripts, scripts to make new initial conditions and things like that. And ExoCAM has grown out of my graduate work over time and has been funded by many different NASA programs, including NESSF, which I think has become FINEST now, and then the NASA Planetary Atmospheres program, Habitable Worlds, SEEC, Astrobiology Institute, and so on. So the goal of ExoCAM is to make exoplanetary modeling, climate modeling, just a little bit easier because it's actually surprisingly challenging to take a nationally Earth-supported climate model and make simple changes, such as your planetary configuration. So how ExoCAM is structured. So in the center here, we have CSM 1.2.1. That is the core code that is being used. It's a Earth-based climate model freely available from the National Center for Atmospheric Research in Boulder, Colorado. And ExoCAM is a patch or an extension that you download and add to the existing CSM 1.2.1. And so ExoCAM is the term I use for it, but it's actually split up into two separate things. There's ExoCAM and then ExoRT. Why separate? Well, radiation, that's really the business end of the changes here to CESM2, because changing your radiation for planetary atmospheres and exoplanetary atmospheres is quite difficult, because these Earth-based models have very streamlined Earth-only, Earth-specific radiation schemes. And I separated ExoRT from ExoCAM so you can run the radiation in a 1D offline mode. It makes it much easier to do development work, to do testing work. So they're technically separated, and then you link them all together within ExoCAM and CSM 1.2.1. And this shows kind of what they all things I've repeated before. I said before that they contain. ExoCAM contains some source code modifications that function to do control things such as the planetary parameters. I've collected them all into a single place. You can change the mass or the radius of the planet, the gravity of the planet, rotation rate characteristics, the stellar spectra, the flux, the atmosphere, many standard things like that. ExoCAM also contains various bug fixes and generalizations for the model. You'd be surprised at how many errant 9.81s or 287s or 28.96s there are lingering that need to be found and changed to something generic that's sourced from a shared module. And then, as I said before, the radiation, that's really the most important part of the upgrade, of having something that's flexible enough to go from multi-bar CO2 atmospheres or include hydrogen all the way up to moist atmospheres and still be valid and tested against a higher resolution line-by-line models as well for accuracy. So what can ExoCAM do? There's multiple configurations available out of the box. I will stress that this is currently a terrestrial exoplanet model, not for gas giants or hot Jupiters and the like. I also note all these little pictures here were all supposed to be animated movies, but they don't seem to be working. They're all still images, but so anyways, they still serve their purpose. So currently out of the box, we have N2, H2O, CO2, methane, and hydrogen. Surface pressures anywhere from 0.1 bars up to 10 bars. Temperatures from 1 to 500 K. Those limitations are predominantly based on the limits of the K coefficients that are built in at the moment. Surface types, right now we have aquaplanet, slab ocean, acuflux ocean, land planets, stellar spectra. There's numerous that are already provided between 2600 K, so TRAPPIST-like, all the way up to F stars. You can change orbital parameters, eccentricity, obliquity, etc. Rotation rate, you can make a synchronous rotators, resonant rotators, change your gravity. You can leverage, with the linking with CSM, you can also leverage many pieces of already generalized physics that are contained in CSMs. For instance, you can run with the finite volume dynamical core, or the spectral element dynamical core, or use the more simple CAM4 clouds, or use the Morrison and Gittleman CAM5 clouds, or use Karma. There's different ways to link ExoCAM with CSM, leveraging some of the physics that's already provided by NCARM. So where to get it? So first you need to download the primary source code from NCAR, and then you can download ExoCAM and ExoRT from my GitHub page. And I will say that I first made this stuff available on my GitHub page in the fall of 2018. Originally, I only put it on GitHub because I needed something to help myself stay organized, and lo and behold, people started using it, and that's when the trouble began. So to date, there have been 46 papers published or on archive by 24 different first authors using ExoCAM either in whole, in pieces, or using large amounts of output to do theoretical observables and things like that. So here's an incomplete list of papers using ExoCAM that have ranged on topics such as paleoclimate Earth, the future Earth, habitable zones, tidally locked planets, looking at different circulation regimes, moist greenhouse climates, FG and K systems, theoretical observers, TRAPPIST-1, TOI 700D, things such as that. So the latest, earlier this, I guess last year now, it's been a year, we published a model description paper, and this was part of the TRAPPIST Habitable Atmospheres Intercomparison Project Special Edition in the Planetary Science Journal. And I like to say that at this point, contributions are welcome to the code, and users have started to send me scripts that are useful for them, or bug fixes, or they find a bug and I have to fix it. But that itself is an extremely helpful thing. So contributions are welcome. Please, if you're using the code and you find something wrong or new, please reach out. I'd love to widen the base of people trying to contribute to the code. So a few things we have under construction right now are CO2 ice clouds and condensation. So what we've done here is port the surface CO2 condensation routines from URADA and Tune from an old MarsCAM model from 2013. And we've also added CO2 condensation from Forget et al. From 1998. He outlines a very simple scheme for CO2 cloud condensation and snowfall. And here are a couple of plots just to show this isn't vaporware. We do have CO2 condensing. This is cloud zonal mean, and then in the integrated column amount, I don't show a surface CO2 condensation plot here. So the status of this is it's pretty close. I'm in the process of tuning and sanity checking. Right now, I get more warming than in Forget et al. 2013 for what I think is the same cloud radii assumption. So I'm still trying to wrestle with that a little bit. There's also this issue that Kitzman has brought up, claiming that CO2 cloud infrared scattering is not good in standard Tune two-stream codes, but and I've had some discussions with people about it. There's not a great workaround to this at the moment. So that's the status for that. The next thing that I'm working on under construction is actually doing fractal hazes again with Karma into ExoCAM. So we're using, and I misspelled microphysics on my slide, so I like to point that out to everybody. So Karma fractal microphysics scheme based on Wolf and Tune 2010, and now we're taking, and there we just had an arbitrary haze production rate, but now we're taking Atmos to produce zenith angle dependent haze production rates and importing it into ExoCAM Karma. And this work has been done by Sandra Bosselberger. We're working on this right now. Here are some plots from a tidally locked planet, Exoplanet Wolf 1069b, where you can see the effective radii, fractal versus sphere, the solid line being global mean, and the spread being all the profiles. And then here is a column amount, and you can see for these tidally locked planets, the hazes end up getting distributed to the night side and having less, right, the substellar point. So the status of this is it's working when I have a globally uniform production rate, and I'm currently getting a weird error, and I'm debugging the inclusion of the zenith angle dependent production rates. So I'm hoping to get that sorted out soon. And then vaporware. These are things we wish we had. So ocean heat transport has always been a very sore spot for us here in ExoCAM land. We use slab oceans generally. There is what's called the POP2 dynamic ocean model that exists in the CESM universe, and it is linkable to ExoCAM. But the problem is it's really unfriendly to use to create new boundary conditions, because the boundary conditions are in binary format, and NCAR provides a 40 bullet point, massive document about you just want to change something very simple like your continents and topography bathymetry, but they have found a way to make it extremely difficult to do. So we haven't done that, figured out those nuances yet. And but we're also interested in perhaps trying to find a middle ground, because dynamic oceans are very slow to spin up. They're not more expensive; they're just very slow to come to equilibrium. About trying to find a middle ground, such as the Cadron et al. 2012 paper, where they use an Ekman slab ocean, where they have some ocean heat transport that is operating in the model, but not in full. So maybe we can get part of the way there without all the expense. So these are things we're thinking about. Higher temperature K coefficients. So Nick Wogan recently created a set for CLIMA up to 2000 K using Helios K. And actually CLIMA and ExoCAM's radiation share the same spectral grid. They share many of the same assumptions. So I've talked to Nick about it. I'm thinking about, with his permission, incorporating these into ExoCAM. It would be pretty straightforward to do, but the impetus hasn't been there. Basically, no one's been, grabbing my ear and saying, I need these, so I haven't done it yet. And then finally, the biggest piece of vaporware, what ExoCAM has sort of outgrown itself and how it's been designed. I would say that originally I put it on GitHub to help myself get organized. What would be really nice to do, now that CESM2 is on GitHub, where CESM1 was not, would be to fork CESM2 into its own Exo CESM and have all the code from ExoCAM and ExoRT already there. So a big refactoring. So users would only download that rather than the piecemeal approach we have now. But really, that's a dream right now. That would be the best software way to go, in my opinion, but would be a ton of work. So I think that's my last slide. Thank you all for listening to my talk today. I'd be happy to take questions.